Like I said, this isn't going to be too crazy because my knowledge isn't the best on this, but I know enough to get by on exam questions. So let's just start with IR. Uh, so let me drop the link one more time for anyone who has an iPad or wants to look as we go along. That's the link to the notes that I'm going to be using. Essentially, all the information I have here is straight from Orgo as a second language. I literally just screenshotted all the pages because I feel like that describes it best. It's part 2 of Orgo as a second language, but it's just telling you all the numbers. So like triple bond, C triple bond N, that's the number you'll see it at. C double bond N, single bond N, all that kind of stuff. I'd say the big one for this is here, just where you're looking at single, double, triple bonds and all that kind of stuff. Uh, don't worry too much about this region. We only really care about that. Nobody cares about that. When you're looking at your IR spectrum, you're going to see numbers 0 to 1500 is the fingerprint region. That's the region we don't care about and we'll never look at. So 0 to 1500, you'll never look at that region. It's just a giant mess. So that's the fingerprint region. What else? What else? Yeah, there we go. Okay. Fingerprint region where you have single bonds. So that's from about 0 to 1500. You're never going to look at that region. The students are just going to have to identify functional groups after that. Okay. Everyone's cool so far. These are the 3 different kinds of single, double, and triple bonds. So the carbon-hydrogen bonds. Normally, you'll see this. This is the carbon-hydrogen stretching at about 3000. This is the single bonds, right? These little fingertip-looking things. What I like to do and what I've learned from this is if you draw a dotted line at 3000, what you'll see is one line is about the carbon double bond, right? So that means carbon's double bonded to something. And that's when this line is between 3000 and 3200. If it's much further left after 3200, that tells you you're looking at some sort of triple bond. Okay. Like I said, this is just a summary of the peaks. The carbon stretching actually isn't all that bad. These guys, however, these guys are important. So this dude, this broad signal, if you see this at around 3600, that tells you that there is an alcohol on your molecule. So let me make that clear. So that tells you there's an alcohol on your molecule. If you have this narrow signal, and I believe the value is about 1600 or so, that gives you your carbonyl group. Those are the 2 biggest peaks that students have to know. That's kind of where they'll see everything. So 3600, and it's broad like this. It may even be a little larger. Usually it's a little bit bigger. That's your alcohol signal. And then your carbonyl signal. I was looking at their lecture quiz, and I believe down here is one of the answers. It says that the alcohols have the broad OH signals, and that's a result of the hydrogen bonding. So I think that might have been on the lecture quiz. I looked at it very quickly. It was just theory stuff, which is awful. Okay, so here is an example of that OH bond, right? So when you're looking at one of these in its full view, I always like to go to the 1500 region and I'll just cross it out. That way I don't make a mistake. So you'll never have to know what's going on over here. And then over here, this is that carbon-carbon stretching. That's just your generic carbon bonds, no single, double, or triple. And then this guy is at about 3600, 3500, and that's telling you that you have your OH there, your alcohol. Okay. Any questions so far? Great question, David. Glad you're participating here. It's No Shave November officially, so there's going to be lots of hair growing everywhere,
Ain't gonna
especially
happen
with
for me.
quarantine.
No, I love having a clean shave face.
All right, David. So now everyone in the world will know how you like your hair preferenced. So here we have two things. The first thing we have is this stretch at about 1700. So this guy tells us that we have the carbonyl, right? And then if you take a look over here, we don't really have that alcohol peak. Does everybody see how normally we have that carbon stretching and then we have the alcohol and there's like this little gap in between? In this structure, they're meshed together. This is carboxylic acid. So when you have this OH peak and the carbon bonds meshing together, you get that carboxylic acid, okay? So really broad alcohol peak along with the carbonyl peak is carboxylic acid. That's the functional group that you're looking for here. If students ask you what IR spec is, just literally tell them it's to identify functional groups. That's its sole purpose. They're not going to be able to determine how many carbons are in a compound from this. They're not going to be able to determine the molecular formula. The only thing that they could determine are functional groups. One of our old head TAs, TJ, some of you may know him. David, what did he call this thing?
Well, the
TJ?
carboxylic, I don't know why, but for some reason, every time they say the carboxylic acid, they say it looks like a nipple.
Yeah, that was
And
it.
the alcohol looks like a mitten. So, but I don't know where they got the nipple from.
Yeah, so like a nipple or a mitten.
Yeah.
Whatever you want. That's your carboxylic acid. That's a fun one to tell your students, you know.
Mm-hmm.
Oh wow. Okay, so that's carboxylic acid. The carbonyl group paired with the alcohol, extra stretching. All right. So here's some practice for you guys. Alcohol, carboxylic acid, or neither. Test your skills. You just type it in the chat, say it out loud, whatever your heart desires. What is on this spectrum? Alcohol, carboxylic acid, or neither? Jay, I read that as O. Like I didn't get that. But you mean it as OH. I got you. It's fine. I'm special. Yeah, awesome. It's alcohol, right? We know that it's alcohol. So if I go to 3000, I have my carbon stretching, carbonate stretch, and then this is the OH group. Cool. See, these aren't that bad. You guys are professionals. All right. Go for all three of these, honestly. So we'll call this 10, 11, and 12. So try those three out. See which group, alcohol, carboxylic acid, or neither. All right, what y'all got for 10? Yeah, exactly. It's neither. 10 has nothing going on. So the first thing you want to do is go to that fingerprint region. Nothing. All we have is the carbon hydrogen stretching, right? There's no functional groups. If we wanted a carbonyl, we would see some kind of peak around here like that, right? If we wanted an alcohol, we'd see something like that. So this one is neither. There's nothing going on. All right, what do we get for 11? Yeah, nice. Liz, I thought you said you were struggling. Professional.
But it just took like a couple of explanations. It's coming back.
No, that's totally cool. That's what it's supposed to do. All right, awesome. This is carboxylic acid. Once again, 1500, cross that out. You have your carbonyl group, and then this is that funky alcohol thing, right? So what you're going to notice is normally an alcohol by itself is over here. When it meshes with the carbon stretching, it can become super broad. So that's your alcohol group. So you have carboxylic acid.
Honestly, Gabby, I cannot forget that picture. It's the reason why I messed up my ester lab. It looks exactly just like it. I'm like, damn, I got a pure carboxylic acid. That sucks.
Yeah, David forgot in the Orgo lab, we did the ester lab. David forgot to filtrate it more than it like enough. So he had like a giant piece of carboxylic acid in his answer. He had like 70% purity. It was awful. Awful. All right, for 12, what do we got? What, alcohol. Orgo lab made me cry once. It's fine. That's why I TA it now, to sympathize with students. I messed up my ester lab. I went to do the separatory funnel and I frickin' the RBF, it was like in 2 hours of lab experiments, and the RBF came undone and spilt all over the bench. And I like cried and had to get a refill from the staff room. Sorry. I don't know why, but Orgo lab just makes me cry.
No, that gave me PTSD.
All right, so we got alcohol here, and that once again is just your carbon hydrogen stretching. So everyone's pretty much got IR down, right? It's not awful, pretty simple. If you're still struggling, let me know, because then I'll just make up more stuff. All right. Here we have, these are just nitrogen groups. I don't really know how in depth Drug Hammer is going to go on this stuff. So these are just your nitrogen groups. This is your primary nitrogen versus your secondary nitrogen. So here it's just showing that 3000 mark and then two small peaks, like two little fingers. Here you would get that stretch around 3400. Okay, so these are just little graphic images of what they look like, just so that you have them on hand and whatnot. All right, and then next are just values. So this is from an old lecture slide. I think these are from last year's lecture slides. These are just where to look for stretching to find different atoms. So it's just saying the carbonyl bond is between 1800. Carbon hydrogen stretching is where we've been looking. And then that OH or NH, those nitrogen bonds, those are the 32 to 3700 region. Okay. Most of this stuff, you know, you guys will just see it in practice. These are just your carbon single bond stuff. So single bonds, double bonds, triple bonds, all of that. If you have a double bond, so your typical alkene, it's going to have a peak between those two values. If it's a carbon-carbon double bond, it has an additional peak at about 1660, 1680. If it's aromatic, then it's going to be those ranges, about 1600. Okay. I know this one came up on a test about 2 years ago. I have that question that we're going to run through to get that answer. So just know that the double bonds will have that stretching accompanied. So will triple bonds. Those guys also have two values. Okay. What else I got in here? This is what a previous exam cover page looked like. So in the olden days, students would get all the stretches along with all the mass spec values. So I don't know if they're giving it again this year. I would assume so. But you know, to each his own. But yeah, these are all the values that we just covered pretty much. Just all the stretching values. So just as long as the students know whether to look for a broad peak, a narrow peak, you know, it'll help them out from there. So does anybody have questions on IR so far? I'm good. Okay. Mass spec is where things get a bit funky. So for mass spec, this is an info sheet. These guys down here are your lifesavers. These are the common mass numbers of groups that you can lose. And I'll talk about what that is in a second. But the three most common are methyl, ethyl, and water, I'd say. Doing all the past exam questions, they really only ever lose an ethyl. That's all they've shown. But anyways, it's basically mass spec is you take a sample, you toss it through a machine, and they break that sample down into smaller fragments. And then those fragments have different masses. They're also going to have that +1 charge. The tallest peak is called your base peak. About 99% of the time, the rightmost number is the total mass of the compound. So you can either look on the mass spec to get the total mass of it, or you can calculate it. Both are totally valid. Chlorine and bromine are two special cases. Chlorine has two isotopes, 35 and 37. On a mass spec, these are in a 3-to-1 ratio. And then bromine is 7981, and those are a 1-to-1 ratio. And I do have an example of each, one example of chlorine and one example of bromine, so you could see what those look like, okay? Okay, so let's just dive into past exam questions. Each question is labeled from where I got it from. And then, what do you call it? English. Each question's labeled from where I got it from, and I don't know what else I'm trying to say. Anywho, this one's nicer. So this is from 2017 final. And I actually have a poll. That way you guys don't spoil the answers for each other. And it's totally anonymous, but it's just so that no one ruins the chat. Shoot. But yeah, so let me know what you get as your compound. So this is from a 2017 final. So this is something students should expect to see. Okay. Everyone vote. Dave, did you vote?
It doesn't allow me to vote, which is weird. It's whatever. I mean, I have my answer. Never mind. Gabby, you're muted.
Sorry, thanks, Dave.
You're welcome.
I like that help me please option. I use that in office hours. I use polls constantly in office hours because it's just so no one spoils it. But yeah, no, help me please. So the answer here is F. Some of you had picked E and some of you had picked A. So here's the deal. When we're looking at this, right? First thing you want to do is get rid of that fingerprint region. And then you want to see what groups you have. So at 3000, you have that carbon hydrogen stretch. And then at this peak here, that's your carbonyl peak. We don't have an alcohol peak, so there's no alcohols involved. We don't have anything going on for triple bonds. If we had triple bonds, there should be a bit of a narrow peak around this region. Okay, we don't have that. The last thing is the carboxylic acid. And we know the carboxylic acid is that mitten looking piece that would be like that. Probably be a lot uglier, you know. So it should just be F because we do have a functional group and it is the carbonyl. Okay. Everyone's okay with that? All right. Go ahead and try out this one. Open up the poll. No, that's not what I want. Darn it. Mina, you're enrolling in classes. I'm sorry. Mad stressful. All right, let's run through this one. So this one's a bit weird with the way it's structured. So for this one, once again, the first thing you want to do is go to that 1500 region. And I know I say it a lot, but it's definitely the easiest thing to do. Just cross that out because that's super confusing to look at. Then you want to come over to this 3000 region and see what's going on. The first thing I like to do is always draw my straight line from 3000 up. So I go nice and straight. It's not really straight. Straight-ish. And what we notice is that we have this little peak over here. Okay. That little peak means something, and I'll get to that in a second. So the first thing we want to recognize is that we don't have any narrow, strong peaks around this region, right? So that means that there are no carbonyls. So that's our first step. No carbonyls. Out, 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 out. Then you're between C and D. So alcohol versus double bond. There's no alcohol peak, right? So that one's also out. So now let's prove why the answer is C. And if you take a look down here, I actually included the stretching numbers. So the carbon double bond, right? That's this peak here. That's just carbon attached to a double bond, right? That doesn't tell the whole story. What you want to look at is this peak where you have carbon-carbon double bond. And that's that stretching at 1620 to 1680. So it's these guys. Those three little fingertips are what tell you that you have a carbon-carbon double bond. Okay, everybody okay with that? So it's those three little fingertips. That's what tells you the carbon-carbon double bond. Okay. Mina, what's bio 337? It just popped up on my thing. Which bio is that?
Neurotransmission. I thought someone wrote in the Orgo group chat, but then when I searched in the conversation, it didn't say anything. So I was like, IDK. But it's neurotransmission.
I think that's the one you need permission to get into, right?
I have no idea. I was just looking at the class eval, and most people got an A. So I was like, but I don't know how much work they put into the class.
I got you. I had a friend who took it, I think. I think she said it was just a ton of essays.
Ooh, okay.
Good luck.
Thanks.
All right, guys. So for this one, once again, it's just those three fingertips that you're looking for that carbon-carbon double bond stretching. All right. Everyone's okay with that? That one's sneaky. I'm not a fan of it. But they've tested it like twice, that same exact region. So that one should be C. Cool. Okay. Go for this one here. Let me zoom in on it for you. So like I said before, these should be all the questions that they come to you with. So at least you guys have some answers to them and hopefully some decent explanations. So when they do ask for help next week in office hours, you'll have these all down. This is exam 3, 2018. Anybody else want to take a guess? All right, let's run through this one. So for this one, the first thing, like I said, you always want to look for those functional groups, okay? So we know at 1500, we're ignoring all of that. The first thing I always like to look for personally is that carbonyl peak, because that's the easiest thing for me to identify. So if I come over here, I'm looking to see something like this, and I don't. I see a baby peak. That's not my carbonyl peak. Those carbonyl peaks are going to be narrow and they're going to be long. So I can't have F. Okay. Then down here, I have all the values, so they're easier to go through. What we see next is we want to look for that triple bond peak, right? Because they have two options with triple bonds. So I'll see if there's some triple bond stuff going on. For triple bonds, you're looking past 3200. So you're looking over here-ish for a triple bond peak, and we don't see one of those. So we can't have any triple bonds. Between C and D, this question was super subtle on it, kind of like the previous one, where you once again go to that 3000 line, draw it straight. Wow. Okay. Draw it straight. You have this little peak over here. So now you have a very small indicator of a carbon double bond. But we don't know what the double bond is attached to. So that's where this comes in down here. If you look, it tells you once again that you have your carbon-carbon double bonds between 16 and 1850. Okay, so this one is super subtle because this guy falls a little bit before the range, but that is what's signifying a carbon-carbon double bond. Okay, the year this test was given, I think the amount of students who got this one correct was very, very small. But those would be the two peaks that tell you that you have a carbon-carbon double bond. So
Wait.
that peak, yeah, go ahead.
Sorry, I'm confused why. Well, I was the help me please category, but I'm a little confused like why you don't have a triple bond because I was thinking maybe you did. Because like when you split it like to the left, you have that would it be further to the left, the peak? Is that what you were saying?
Yeah, so you want this peak to be further. You want it to be about over here-ish.
Okay.
And then you also want to have the additional peak. If you look right here,
Mm-hmm.
you want it like 2100.
Okay.
So it's just a little two to the right here because it's at 1641.
Okay. Thanks.
Yeah, of course. Yeah, like I said, this question was awful that year. I think most students got it wrong.
Hey, Gabby.
Yeah.
Sorry, would you mind what would it look like if it was E? Like what would that second peak be looking like on the right?
Let me see. Let me check what the numbers for aromatic were again.
Okay. Sorry, because I saw that there was a double bond, but I was confused as to whether it was like in like a the benzene ring or something, or whether it was C.
Yeah, no, you're totally good. So aromatic is 1600 and 1475. Thought I had another slide with a better aromatic thing. Yeah, no, same value. Okay. So aromatic ring, if I'm not mistaken, I believe it needs to have 3 fingertips along like that region. Does anybody remember what the aromatic looks like?
I think there was a question. I'm not sure if you have it, Gabby.
Yeah, I got it.
It showed a peak with a benzene ring before.
It's I think the benzene ring was the mass spec question though, not the IR.
Oh, okay. My bad.
No, you're good, Dave. Yeah, okay. So I'm looking at it now. So with the aromatic, let me pop it up real quick. So the aromatic has these things that they call overtones. Enlarge. There they are. So they have these overtone guys. And I don't know if you could see them where it says overtones because I can't really point on this. But yeah, those overtones. So aromatics will have like those 3 or 4 fingertips.
Okay. All right. Cool. Thank you.
Yeah, of course. It was a good question. All right.
Wait, Gabby, I don't know if this matters, but you said like before that the three peaks also are related to the double bond for the alkene. So does that have to do anything with the benzene ring too?
No, the benzene ring will have this peak over here, and then it should also have those three fingertips. All right, so let's go into mass spec a little bit. Mass spec at first is overwhelming, but then after that, it becomes easier. It's just a lot of math. So for mass spec, they want us to draw the structure of the cation that corresponds to base peak at a mass of 57. So the first thing you want to do in these questions is get the mass of the entire compound, right? And like we were saying before, there's two ways to accomplish this. The first way to do it is to literally calculate the mass. So I'd go carbons, oxygens, hydrogen. Carbon weighs 12, oxygen weighs 16, hydrogen weighs 1. Multiply them by how many there are. So for carbon, 5, 1 oxygen. Hydrogens are 3, 6, 10. So mass spec is really just math. 60, 16, and 10. Add those up, you get 86. So that's the first way to find the mass of the compound. The other way is to just come over here. It's a little blurry, but if you take a look, it goes 80, 85, 90, 95, 100. So if you know that this is 85, this is 1 over, so that would be 86. So the rightmost peak will tell you the mass of the compound 99% of the time. I don't think I've ever personally seen that not work, but if you have the compound, there's no harm in just calculating it. The next thing you want to do is you want to see in this question what the compound looks like at a mass of 57. So that means you have to start removing carbons until the mass of your compound drops from 86 to 57. So the best way to go about that is to literally do 86 minus 57, and you get 29. If you go back to that cheat sheet that I gave you with all those highlighted numbers, these guys, you'll see that 29 means that you lost an ethyl group. That's where these numbers start to come in handy, is when you start getting them as values. And you could say you got 29, so you had lost an ethyl group. So now we're going to take this structure that they give us, and we need to chop off the ethyl group. So we're chopping off this group here that's boxed, right? That's a CH2, CH3. And your result is a positive charge on that carbon. Every time you chop, you get a positive charge. That's an awful looking structure. Those don't even look like carbons. What am I even doing with my life? Okay, so you get that positive charge. Now, like David said in the chat, this isn't the most stable form. In these cases, oxygen forms what's called the acylium ion. And what that means is we have this positive charge on a carbon-carbon double bond. So oxygen actually takes a pair of electrons and drops them to form a triple bond. With these questions, always count your carbons, because you'll always lose them with the triple bonds. They get kind of weird to draw out. So here we have 1, 2, 3. Oxygen has one lone pair left, so it gets a positive charge. And this is called the acylium ion. For students to get full credit, they must draw the acylium ion. I believe if they leave it in this form, they lose points. And that would be your answer. So in mass spec, you're just chopping groups off and getting a positive charge, and then that's the answer. That makes sense to everybody? Any questions? All good. All right. This one was actually from a 2016 final exam. So the students don't have access to this one. So if you're looking for an extra question to give them, this one works. All right, let's go for this one. So this one, they want the ion at 105. Why don't you all try it? Go ahead and try to draw a structure, and then I'll go through it in a minute. Also, I hope y'all are finding this helpful. I know Orgo's boring, but we try.
Thank you, Gabby.
Oh yeah, of course, anytime.
I don't know, for some reason, I can never remember any of this stuff. It just comes in and it just goes out.
That's how I feel about Orgo too. When you reach like that one chapter in Orgo 2 with like Curtius, Hoffman, like that whole area, it's like 20 mechanisms and it's all a blur. All of it. Yeah, no. For some reason, I can kind of remember HNMR, but even that goes.
No, HNMR is like my weakest point ever.
I watch mad YouTube videos on HNMR. All right, does everybody have a structure? What did you guys get for the total mass of the compound?
I got 134.
Yeah, awesome. So the total mass is 134. Once again, I think it's a little blurry, but if you come down here and you just look at it, it goes by 1. So it's 26, 27, 28, 29, 30, 31, 32, 33, 34. So it's 134 is the mass of the compound, that rightmost peak. Or you can just go ahead and calculate it. So if you do decide to calculate it, you get carbons, hydrogens, oxygens. And then I always do the mass number first. I don't know why. And then I multiply it by how many there are. So carbons, there's 6, 9. Hydrogens is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And oxygens is 1. Put little H's here. So then you do math, 10, 16, is that 96? 12 times 9? 108. Close. Plus 10, plus 16, 134. Alrighty. And then they want the mass at 105. So then you just subtract 134 minus 105 and you get 29. So once again, we're losing an ethyl group. So when you chop off that ethyl, it's just going to be this guy here, right? You get a positive charge on that oxygen with the double bond. Oops. Oh boy, I'm jumping ahead. Okay, here we go. 300th time the charm. Get that guy, not the most stable form. You have to make the acylium ion. So then we would have to drop down. And they have to show that triple bond. And then count your carbons to be sure. 1, 2, 1, 2. Everybody get that for this one? Okay. And students will probably ask you if they have to draw this in Oscar sketch. It's totally valid. They do have the pre-made rings at the bottom and the benzenes and stuff like that. So I could totally see them having to draw this in Oscar sketch. Any questions? Okay. Hopefully after you do it a few times, it becomes a bit easier. All right, this is exam 3, 2018. So go ahead and try this one out. And this one I could actually pull. So one thing I do want to mention for this one is you have two values next to each other, and the ratio is 1:1. So that 1:1 ratio, do you guys remember which compound that is? Yeah. So this 1:1 ratio tells you that you have a BR in your structure. So if students know that, it's essentially a 50-50 shot. Okay. So you have that 1:1 structure. So see if you can figure that out. The reason we know it's bromine is because bromine has two different isotopes, 79 and 81, I believe. Yeah. If you guys need help on this one, let me know.
I need help.
Yeah, no, totally fine.
Help, but my poll disappeared.
No,
I'm confused.
not funny. Okay, so for this one, right, it's the 1:1 ratio, and we know it's 1:1 because these peaks are super close together. They're almost identical. So that tells us BR has two isotopes, 79 and 81. Because we know it's BR, we can get rid of everything except for E and F. The only thing you have to do in this problem, which makes it more of like a simple one once you realize it, is just calculate the molecular weight of E with both isotopes, calculate the molecular weight of F with both isotopes. And then one of them will add up to 156 and 158, and then the other one only adds up to one of these values, but not the other. It's sneaky and rude. But so let's go for E. So with E, we have C6, H5, Br. So we have two isotopes. So carbons 12, 1. We'll do 79 for bromine. We have 6 carbons, 5 hydrogens, 1 bromine. So 12 times 6 is 72. 5, 79. Add all those up. 156. So that value checks out. Now you want to do the same math, but you want to use the isotope with 81. So then you'll just do 72 plus 5 plus 81. And then those guys, you get 158. So for E, both values check out, right? That equals the total mass of the compound. When you go to do F, F is going to be a bit off base here. Carbons, hydrogens, bromines. So carbon is 6, hydrogen is 7, bromine, there's one of those. 12, 1, 79. So 6 times 12 is 72. 7, 79. And that equals 158. So that value also checks out. The last thing we need to do here is check for that other isotope, right? We got to check for isotope 81. So then we would do 72, 7, and 81 and add those up. And that gives you 160. So that isotope does not check out. That's why F is incorrect and E here is the correct answer because you need to account for both isotopes of bromine.
So for this one, you don't necessarily even have to look at like the big peak at 77. Like if you were to break the BR off, like what is the big thing at 77 referring to, I guess?
So 77, that's your base peak. So if you were to do 156 minus 77, you get 79. So this is telling you that you lose a bromine in between here.
Yes. Never mind. Yes.
You sure?
Yes. I thought it was supposed to say 79. Like I forgot. Sorry. Okay, yes.
No, that's okay.
I'm back. Yes, okay. We're good. Thanks.
Yeah, of course. Yeah, so the difference here is 77, 79. 79 is the difference there. So you'd cut off a bromine, and then you can add up the remaining. This one will equal 77, that one won't. But I think this way is a lot easier. I don't know. It's just, I like the math part of it. I'm a nerd. Okay. Everyone's okay on this question? Yeah, all right. We got 2 more left and then we're done with this topic. And these are all the past exam questions that I could find. I went through finals, I went through exam 3s and exam 2s. So there's not much on it because a lot of the IR stuff is grouped with CNMR and HNMR, and they haven't learned that yet, so we can't use any of those questions. I think this is from your guys' exam, actually. I think this is exam 2 2019, if I'm not mistaken. Right? Yeah, you guys are 2019. Oh, how long ago it feels. All right, anybody know which functional group we're dealing with here? Yeah, Cl. I don't know if you could see up top, but it literally tells you that it's a 3-to-1 ratio in the question, which is really sweet of them. So because it's that 3-to-1 ratio, we know that we need a Cl. So you cross out everything else. And Cl has 2 isotopes, 35 and 37. So what I would recommend doing for this question, one of 2 things. You can take this guy, use both isotopes, see if it adds up to these numbers, right? Because the rightmost number is going to be the mass of the entire compound. And then do the same thing here. Add up the mass of this and see if it matches those numbers. It's essentially the same thing we just did for bromine. All right, does that make sense to everybody? Y'all okay? So if we go for D, so for D, we have, what do we got? Carbon, hydrogen, and Cl. So carbon is 12, 1, 35. 3 carbons, 3, 6, 7 hydrogens. Common mistake is missing that H there. And then chlorine is 1. 35, 7, and 12 times 3 should be 36. Let's see, 12 times 3, yeah, 36, 7, 35. So this dude gives us 78, right? So that checks out. These are my magic numbers here. So then you want to do it again, do it with the 37 isotope. It should equal 80 because it's 2 more, but let's just double check. So then you get 36, 7, 37, and that's 80. So both isotopes check out for D. All right, does everybody get the math I did there? Here, the numbers stay the same. I'm just changing the isotope. Okay. Then we can go for F. And F, it actually becomes super clear that it's not going to work because there's a whole carbon missing. So you got 12, 1, 35, 2, 5, 1, 24, oops, 5, 35, 24 plus 35 plus 5, and this is 64. right? So that's nowhere near 78 or 80. So that's how we know F is not the correct isotope. And then it should be D. Everybody okay with that?
How can you tell if it's a 3-to-1 ratio if the question doesn't tell you? Or will they always tell you?
No, that's a good question. So what we saw with the BR question, right? It's a 1-to-1 ratio. Here we knew it was 1-to-1 because they're almost exactly the same height. For the 3-to-1 ratio, you should have one peak that's about 3 times larger than that small peak.
Oh,
So
okay.
it's like 3 of these stacked together should equal that other peak.
All right. Thank you.
Yeah, of course. And I mean, from what I've seen, anything that gives you two numbers right next to each other, you're usually going for isotopes. It's just a matter of Cl and Br. They probably said 3-to-1 ratio here, I guess, because it was unclear. I'm not sure. Maybe they're just being nice. All right, good with that. Yeah, all right. Last question. This is from 2019, the final exam. This is something I feel like they may get on their test because it combines IR and mass spec. So now they have to use them together. So let's focus on the IR first. Which functional groups do we see in the IR? Could zoom in more. Oh, you guys answered already. What am I doing with my life? I'm like sitting here waiting like I'm special. Yeah, it's a carbonyl, right? Because once again, you ignore this region. Garbage. This dude, your carbonyl peak. Awful circle. Carbonyl. This is just your carbon-hydrogen stretching. Awesome. So we have a carbonyl, right? That's the first thing we've learned. So right away, I just cross everything out. That's not a carbonyl. Okay. Next, you want to look at the mass spec, right? What does the mass spec tell you? It's telling you it's a parent peak. Take a look. You see how these numbers are 178 and 180, right? Yeah, it's that 1-to-1 ratio. So this parent peak is a 1-to-1 ratio and the numbers are 2 apart. So that's indicating a BR. So 1-to-1 ratio. And the fact that the numbers are 2 apart. Right? Because remember, the isotopes for bromine and chlorine. Bromine is 79 and 81. So those are 2 apart. Same thing with chlorine, 35, 37. If this was chlorine, I could see this one only going up to maybe there. Right? If you ignore that green part and just pay attention to the red part, that would probably be something like a chlorine peak, like a 3-to-1 ratio. But because they're about the same height, that's that 1-to-1 ratio that we're looking at here. So from this, once you figure out that that's bromine, you could pretty much eliminate everything else. And you just get E. So you just have to identify the functional groups here. Any questions?
Could you knock off C just from the IR if because we don't see that like broad carboxylic acid peak or no?
Yeah, definitely.
Yep. Mhm.
Okay.
Yeah, so then in that case, it's just a matter of whether you're dealing with Cl or Br. Exactly. Like I said, Cl would probably be something like that.
What are the little like baby green things at 179 and 181? Like, are those irrelevant? Like,
I would say that there are other isotopes.
okay.
So maybe one, like these guys, maybe like the 79 isotopes or maybe like the 81 isotopes, something like that. They may still be relevant because they are that 1-to-1 ratio still.
But you wouldn't compare like the 178 to the 179 because you need one that's things that are 2 apart.
Exactly, yeah.
Okay. Got it.
Okay. Any other questions, guys? All good. Okay. So last thing is at the end of this, I have practice questions for students. So if you guys find you need more questions, this is basically just, they have a ton of compounds, they have a ton of IR specs, and they could match them. And then at the very end is all the answers for them. So just if you need something to do with office hours with some good IR practice, these are just some good practice questions. But that's really it for this. That's all I have. So do you guys have any questions at all on any of this crap? All good. Informative, hopefully, makes more sense. It's next week's workshop, so you have enough time to study it some more if you need it. I think it's next week. I thought it was this week for some reason, but it's not because I'm special. But yeah. All right, guys. Awesome.